Hey, welcome back. Let's introduce another powerful approach, Hamiltonian equations. In previous lessons, we saw that if the Lagrangian does not depend on a specific generalized coordinate q, then its generalized momentum is conserved. This generalized momentum could be written as the partial derivative of the Lagrangian with respect to the velocity q dot. We also saw that if the Lagrangian does not depend explicitly on time, then energy is conserved. For that we wrote the function h as the sum of the partial derivative of the Lagrangian with respect to q sub I dot times q sub I dot minus the Lagrangian. This function h we call the Hamiltonian of the system. Knowing that the generalized momentum is the partial of L with respect to q dot, we can rewrite the Hamiltonian as the sum of pi qi dot minus L, while the Lagrangian depends on the generalized coordinates, its velocities, and time. The Hamiltonian is a function of the generalized coordinates qi, the generalized momenta pi, and time. Remember that the generalized coordinates can be the Cartesian coordinates, but could be any combination of coordinates that help describe the system. With this in mind, let's differentiate the Hamiltonian. We write dh as the sum of the partial of h with respect to the coordinates q differential of q plus the partial of h with respect to the momenta times dp plus the partial of h with respect to time dt. Now, using the definition of the Hamiltonian, we write also this as the sum of q dot p dp plus p dq dot minus the partial of L with respect to q dq minus the partial of L with respect to q dot dq dot minus the partial of L dt. Using here the definitions of the generalized momenta and their derivatives, two terms cancel and we write this as dh equals to the sum of q dot dp minus p dot dq minus the partial of L with respect to time dt. Let's now compare these two equations. We can identify the following two identities. Q dot is equals to the partial of the Hamiltonian with respect to p, and minus p dot is equal to the partial of the Hamiltonian with respect to q. These are called Hamilton's equations of motion or canonical equations. And they can be used to find the equations of motion of a system. They are equivalent to Lagrange equations and therefore they are equivalent to Newton's second law. Remember that we had already found that if the Hamiltonian does not depend explicitly on time, the Hamiltonian is a conserved quantity, and if the potential does not depend on the velocities, then this conserved quantity is the energy of the system. Look that here we have, for its generalized coordinates, two equations. These equations are first-order differential equations. In the case of the Lagrange equations, we had only one equation per generalized coordinate, but that was a second-order differential equation. Let's see some examples now. Consider a simple pendulum and let's write Hamilton's equations. First, we need to write the Lagrangian. We'll consider the pivot to be at the origin of the coordinates. The kinetic energy then, written in polar coordinates, is 1/2 ml square theta dot square. The potential energy is minus mgl cosine of theta. And the generalized momentum for theta is the partial of the Lagrangian with respect to theta dot, which is ml squared theta dot. To write Hamilton's equations, I have to change the velocities by the momenta. So here I have that theta dot is equals to p sub theta over ml squared. So the Hamiltonian is p theta theta dot minus L, which is p theta squared over 2ml squared, minus mgl cosine of theta. This is in fact the total energy of the pendulum. Double check that. Now the equations of motion are theta dot equals to the partial of h with respect to p theta, but that's what I already had, and p theta dot equal to negative the partial of h with respect to theta, which is negative mgl sine of theta. Playing a little bit with these two equations, we get the equation of motion we expected, the same we found with Newton's second law and the one we found with Lagrange equations, of course. May Hamilton equations be with you.